Welcome to the second part of the structural and functional properties of the elements in geometrifying trigonometry. We know that after Richard Dedekind converted the numbers to the number line, and world tried to move towards the number line representations, and then new kind of analysis started. After 1870, when Felix Klein started the Erlangen program in Göttingen, which tried to bridge between the different subjects of geometry with different subjects of number theory, and different subjects of analysis were connected with different kinds of geometry. Then elliptic curves came and different analysis styles changed. When we go through the papers of Cantor and Dedekind, and if we go through the letters between George Cantor and Richard Dedekind, then we find there was a discussion regarding how to represent numbers in geometric way and how to represent geometry in number system. These kind of discussions were going on, and after 1900, when David Hilbert's important papers came out with the 23 problems were focused, and David Hilbert wrote an important book regarding the geometry and imagination, where he explained from page number 59 to page number 100 regarding several such aspects of the dream to represent trigonometry also as geometry, and geometry is already a part of trigonometry because trigonometry deals with triangles, but trigonometry expressions are like algebra. From Richard Dedekind to Cantor to Hilbert and also Bertrand Russell, everyone had a dream to grab the things in a more formal way, and Felix Klein tried to represent everything with the geometry and geometry with number systems. He had a dream that someday this bridging is possible, and the time computer was not there, and we are lucky enough that we are now in the stage where large language models are also working, and we have found the attention systems which are reading human languages and can represent it in a different way. The rewriting systems are also working. In 2000, around 2000, from 1994, that was a dream from Sanjay Nath's side, was that to visualize everything with geometry for trigonometry expressions. But at that time Sanjay Nath was not the CAD programmer, so he was not aware of how the CAD systems can give the better insights on trigonometry expressions. And from 2000, when Sanjay Nath started working professionally on the CAD systems, then he found that line segments are representing trigonometry expressions very well, but the formalization is not easy. It took long time to formalize the parts of trigonometry expressions such that the trigonometry ratios can represent like triangles, and triangles are representable as trigonometry ratios. It took time for Sanjay Nath to formalize the things with strict naming of points of a triangle, the strict naming of the line segments of a triangle. In Sanjay Nath's geometrifying trigonometry, the 6 elements are very fundamental to describe the structural and functional aspects of trigonometry. The 3 line segments are generalized for trigonometry. The 3 line segments are input line segment, output line segment, and complement line segment, because the division operator and the multiplication operator of arithmetic are not describable formally until the output line segment divided by input line segment is formalized. So division is a important property, an important functional property for any algebra-like systems, for any number system. So to represent numbers as triangle or to represent triangles as number, the fundamental functional units are multiplication and division, where multiplication is well defined with the line segments and triangles are glued, and division is just a reverse thing, but not look like reverse in geometrifying trigonometry. It is the division of one line segment by another line segment to generate a triangle. Triangle is the fundamental unit of GT simplex, where this triangle is made up of 3 line segments, where output line segment is divided by input line segment, means the input line segment is transformed into output line segment within a single triangle, and in the process the complementary line segment is also generated, like this. If this is the input line segment, suppose in the last video also we have shown that there are 2 line segments, and from that we can represent that. Since we are opening the text here, it is not grabbing the right points properly in GeoGebra, and GeoGebra hangs in those cases. And GeoGebra is also not very good software for trigonometry visualization, because several functions which are necessary to prepare recursive constructions for GT simplexes or to construct the locked sets are not available in GeoGebra, because these functions are not sufficient. Only these kind of options are not sufficient in the GeoGebra. Functions are not sufficient to handle geometrifying trigonometry. Geometrifying trigonometry needs several more functions, like reflection about any given line segment, with reflection about the perpendicular bisector of a line segment. Geometrifying trigonometry need the recursive constructive protocols. Suppose one GT simplex is prepared due to the gluing of multiple line segments, multiple triangles with the common edges. This functionality is not available in GeoGebra yet. So if these functionalities come, when Sanjanath is making a list of the functionalities that are necessary in GeoGebra to do geometrifying trigonometry better. Otherwise, Sanjanath is generating several JavaScripts on GeoGebra such that people can play with geometrifying trigonometry on GeoGebra also. And there is a separate simulator of automated trigonometry in Autodesk Forum, where we get these kind of functions, and with that we can visualize GT simplexes, we can visualize the locked set, we can visualize the plus minus into divide in GT simplexes. Today, in our structural and functional part of geometrifying trigonometry, we will discuss here regarding the construction of numbers as triangles, the construction of triangles as number. Those are already covered in previous videos. So we will start with the structural and functional aspects of number systems, real number systems, and where it is a little bit changed in geometrifying trigonometry to cope up with the transformation of a number to a trigonometry object and a trigonometry object to a number. Here are some options. Up to the last video we have discussed regarding the order structures of the real number systems, and that is already covered in geometrifying trigonometry, such that we can order different GT simplexes, we can get the ordering of every locked sets also through the output line segments. That is already discussed in previous video. Today we will start with the completeness of real number system. That is complete, meaning that it has no gaps or holes, and this property ensures that any non-empty set of real numbers that is bounded above has a least upper bound or supremum. From Dedekind's cuts and from the line real line representation after Richard Dedekind has made the number systems real numbers on the real line, we have seen that the line is continuous, and on that all numbers, either it is rational number or irrational number, they are continuously placed, and there is no gap, no hole on the line, on the number line. And this same property also holds for GT simplexes. We can think that any output line segment, any line segment can have any length. Either its length is rational or either its length is irrational. We have seen that the diagonal of a square is irrational number, that is √2, which is irrational, but that line segment is drawable. So we can guarantee that many kind of numbers which are irrational and still they are constructible. And so if it is not constructible, then we can make arrangement to keep that irrational line segment as a fixed line segment on a HEP locked set. HEP means from the three fundamental persons, the three first persons, the Hipparchus, Euclid and Pythagoras. HEP means Hipparchus, Euclid and Pythagoras. Sometimes Sanjana says it as the THEP, the THEP arrangement, that is the Thales, Hipparchus, Euclid and Pythagoras. From these names, THEP arrangement is made, where we can keep any line segments pre-constructed and keep it as a fundamental element, as a fundamental locked set with which we can start constructions. And in that locked set, Sanjanath identified 43 line segments are necessary, but 3 line segments is the triangle, which is most fundamental structural and functional unit for geometrifying trigonometry, and line segment is the interactor object, and that is also a structural and functional part. But without triangles we cannot think about trigonometry. So triangles are the most fundamental structural and functional units of geometrifying trigonometry. Until we can see any triangle, we cannot intuitively say that it is the subject of trigonometry. Obviously it is from the definition of THP, that is from the definition of Thales, Euclid, Pythagoras and Hipparchus. We can not say the subject trigonometry without the concept of triangles. In that way, completeness is possible in geometrifying trigonometry. Any number is factorizable, that is, there can have the factors, or the numbers can have the partitions, that is, that they are addable. If we represent any number as the factors of multiple numbers, then we take it as the GT simplex, and if the number is represented as the partition, as a summation of multiple numbers, then we can consider it as a locked set. This is important point here. When multiple GT simplexes are added or subtracted with the output line segments, alignment systems, then a locked set is formed. Again, every GT simplex has a common given line segment. For every locked set has also that same common given line segment L, but the output line segment for different GT simplexes can take different positions, can take different lanes, can have different orientations. Similarly, for the output line segments of locked set can have the different positions, different orientations and different lanes. So I think people are now clear that we handle the output line segments and it is at par and consistent with our daily life trigonometry, because our daily life trigonometry also handles the length of the line segments. Ultimately, the definitions of the trigonometry ratios are nothing but the lengths of line segments are taken in a ratio, like hypotenuse by base or base by hypotenuse. What we do actually the length of base divided by length of hypotenuse is cos theta. Ultimately, there is a ratio, which means when we know hypotenuse but we have to find the base, then we multiply hypotenuse with cos theta. This terminology is rephrased or rewritten in Sanjana's geometrifying trigonometry as if the denominator is known, like hypotenuse is known and base is not known. So the unknown is kept on the numerator and the known thing is kept in the denominator. Then this transformation is journey from the known thing to the unknown thing. So the given line segment is at the denominator and that is the input, and the output line segment, which was not known before the ratio is multiplied, so that not known line segment is now generated due to the division. And in this way, the base and hypotenuse are the part of the line segments and perpendicular is now the complement. So all these three makes the ratio actually, and that ratio is actually a triangle. Geometrifying trigonometry describes this division process in that way. So whenever we see any GT simplex is divided with the GT simplex, then we assume that, and it is well defined now, and the algorithms are possible to develop to construct geometry out of trigonometry expressions, because we have rephrased it, we have redefined the concept of division in terms of the output line segment divided by input line segment, as if the input line segment is given, so we could achieve the output line segment due to the multiplication of a trigonometry ratio. So the trigonometry ratio is not a ratio, it is a transformer which generates an output line segment from any given line segment. In this definition, we can take any ratio as a rational number, and irrational numbers are also approximated rational numbers in practical world. In engineering practices, we take up to 6 decimal places or 11 decimal places and we get the things done, and for the high precision arithmetic we do it up to 60 decimal places, but we don't take it up to the infinite decimal places. No practical work is done in the CAD industry with that kind of infinite decimal places. So for the finite decimal places cases in the practical world, we can already take it as a ratio of two numbers, since we are already working with the finite decimal places, because our floating point arithmetic processors are supporting up to that, and we have already reached Mars, and we have already developed the space mission systems, and such that we are grabbing big pictures from the out galaxies. With that limitations, we are not taking any infinite decimal places to achieve these things. So in our real daily life problems, we can assume that 6 decimal places or 11 decimal places is sufficient to handle with the irrational numbers. Let mathematicians think about the infinite decimal places. We engineers are bothered only up to that 11 decimal places right now, and in that way everything are rational numbers. And okay, if we think that there are the holes or gaps in the real number line, engineers are not going to bother that much. Because that is not practically applicable. When the students are not getting any option, when engineers are not getting any options to diagrammatically represent the trigonometry objects, the triangulated objects from given trigonometry expression, we cannot do that daydream that until we will get up to infinite decimal places, then only we will work on the trigonometry geometrification. That is not the good thing to think about when we are trying to find any practical solutions for real life. And many people are not understanding that the structural engineers or jewelry designers or fashion designers or even the graph theorists and will get lot of benefit due to these kind of triangulated representations of trigonometry expressions. Let them get the benefit first, and let some commercial activities go on with those things. And even for the DNA structures or the RNA structures analysis, we need the geometric representations of the trigonometry expressions, because several kind of signals we are getting in the biological analysis systems or the biotechnology systems, we are not getting the diagrams, and so our intuitions are not going up. So first our purpose is to make some diagrammatic representations of the trigonometry expressions. Let that is done. Let we get some good kind of simulators such that we can play with the geometry, such that we can ask geometric questions to the trigonometry expressions, and we can ask some trigonometric questions to the geometry expressions. And these kind of things, the two-way process should start first, and after that we will think about the infinite decimal places cases. Now the functional property needs in the real number systems relate to its utility and the operations of the functions it can support, and these properties include the arithmetic operations. The real number systems support the arithmetic operators such as the addition, subtraction, multiplication and division, and also equality checks. Now addition, subtraction, multiplication, division of numbers are following commutative laws, associative laws, distributive laws. But while we are trying to construct these things geometrically, suppose if we have to draw a right angle triangle from the given hypotenuse, suppose. Now when hypotenuse is given, then first we will take the midpoint of that hypotenuse, then we will draw a circle about that such that the hypotenuse becomes the diameter of that circle. Then we will take a point, either the first point of the hypotenuse, or we will take the second point of the hypotenuse. Now if suppose the theta angle theta is given, we can draw a seed angle on the right side of the given hypotenuse or towards the left side of the given hypotenuse. Similarly, we can draw the angle theta at the right side of the end point of hypotenuse or on the left side of the end point of the hypotenuse. In that way, we can draw 4 line segments, and these 4 line segments cut that previous circle. Now, and where it cuts, that point is the nodal point. That point is the stage point, sorry, because at that point the maximum angle is formed, and that is 90 degree. And when we will connect this start point with that point and end point of the diagonal with that point, then we will get the 4 different symmetries of the triangles. So anyone knows the hypotenuse, and if he has to draw the base and perpendicular for any given theta, then all 4 options are right options. So as per Felix Klein's 4 symmetry rule, for every construction of plus, minus, into, divide, at every stages we see the 4 options open up. Here we cannot do these geometric operations in a commutative way. We cannot draw the circle first and then we take the midpoint. We cannot do that. We have to follow the geometric protocols in a left to right rule. We cannot shuffle that. So plus, minus, into, divide, anything we do in geometrifying trigonometry, in the geometric operations, that is not commutative. That is associative, okay, that is distributive, okay, but that is not commutative, because geometric constructions are not at all commutative, like arithmetic operators on the numbers. Triangles are represented as the numbers, and numbers are represented as the triangles in geometrifying trigonometry. That's okay. And we have already said that we can already easily prove that the continuity of no gap, no hole case, the completeness of number system is also easily provable through geometrifying trigonometry, because the length of line segment can become rational, irrational, or whatever in the number line, and there is no hole, no gaps, and everything are constructible. Even if it is anything, it is constructible. We are working in that way, and we have already said that up to 6 decimal place or up to 11 decimal place it is sufficient. So our number line is a grid like thing, and anything between of the larger decimal places are not considered in this scenario, and still it is practically very applicable. We are not too much bothered yet. Currently we are not bothered about the things where there are 6,000 decimal places necessary. We are not bothered up to that right now. Now plus, minus, into, divide are all following a quad tree, because for every operator there are the 4 options open up due to the 4 symmetries are constructible, and all are correct, all are equally correct. We cannot say that any of these are not equally correct. Now one point comes here is the Lagrangian mechanics and the Hamiltonian mechanics, that if some arrangement takes more energy and if some arrangement takes less energy, then the least energy principle can work, and in that way we can describe some theory with the quantum mechanics, where we can find that entangled line segments will take the minimum energy principle, and that is a different subject, and that will add the additional research on the geometrifying trigonometry, where which of these configurations will give us the least energy principle to construct it. We will talk about it in the later videos, where some of the line segment configurations will take the least energy to construct, and some of the arrangement will take more energy. That is a different way to do research, and the geometric queries will come up with those kind of theories also. Now the continuity part of this functional analysis, the functional properties of geometrifying trigonometry, the continuity, the real number system is continuous, meaning that it allows for smooth transition between the number without any sudden jump or discontinuities, and this property is essential in the calculus and analysis. Yes, obviously anything up to the 6 decimal place or 11 decimal place is a sufficiently small number, and in practical cases we can take it as continuous, and our system can have a very less value of theta. In our simulator also it takes up to the 0.000001 degree, and that is sufficiently small, and with that also we can do calculus, sufficiently good calculus, and up to 11 decimal places we can handle it. To the micron level of grinding machines we can work on that also, so it will suffice for our continuous curve manufacturing with for the car hoods or for any kind of spaceships, or to calculate the spatial movements. That is we think that is sufficient for our working, and so we can take it as a continuity, and the discontinuous properties are always there for some cases where the reflections are there, and in that case the double of when we take any line segment is reflected about any line segment and the theta is very small, still it becomes double. When it is reflected, the distances is doubled, and those kind of jumps are there, and that is also a different aspect of the analysis for the functional due to the functional properties of these geometric constructions. And obviously in CAD we are not using the ruler compass, we are using the CAD. In that case very micro level detailing is also possible, and we can consider the theoretically the ruler compass mechanisms are used. Physical compass cannot draw so micro level drawings, but CAD can draw that. In this way we can think that our structural and functional aspects of elements like line segments, like triangles, are all easily covered in this system of triangles. So fundamentally we will consider that we will focus on the output line segment when we will do the plus minus, and for the case of into and divide, while we will do the multiplication and division, we will take it in a different way. Like the gluing is the most important concept for multiplication, and for division that is also gluing, but the gluing at the points, not at the line segments, and that gluing causes a construction of a triangle. But there are several hidden jungles of line segments always come with the output line segments of any GT simplex or for any locked set. Obviously for anyone in this video I want to tell you that whenever I am talking about any GT simplex, always assume that there are a large number of line segments are entangled together, like Delaunay triangulation kind of objects is there. And when multiple Delaunay triangulations are added one after another, where it can happen that they are just touched at any vertex and no edge are overlapped, these kind of things happen in cases of the locked sets. But for the GT simplexes, there are surely several line segments are overlapped on one on another, and in that way it looks like a Delaunay triangulation kind of object in case of GT simplex. But in case of locked set, suppose sin theta plus cos theta plus tan theta, in that case sin theta is GT simplex, cos theta is a GT simplex, and tan theta is a GT simplex. They are added at the output line segments are added. Suppose in that case we will take the L as the hypotenuse and we will construct perpendicular, that is the sin theta. Now L, the same line segment L is taken as the hypotenuse and the base is taken, which is the cos theta. Now for the same line segment L we draw a perpendicular on that with the C triangle theta, and that is the tan theta. In that way, when these three output line segments are placed one after another, suppose the end of cos theta or the end of sin theta line segment, we are placing the start point of the cos theta line segment, and then placing at the end of the cos theta line segment we are placing the start of the tan theta line segment. And when we are doing this, the other triangles are also coming with that, because we cannot separate the output line segments from its GT simplex. It carries all the GT simplex line segments together when it is moving anywhere on the plane. So in a locked set we will assume that there are a large number of other line segments also present there, and these line segments also interact with each other, and several geometric theorems will come up. In the same way, when we multiply any GT simplex with another GT simplex, obviously both of these GT simplexes are constructed from the common given line segment L, and both of these GT simplexes are constructed in that way. I should give you a simple example for that. Suppose we are considering tan theta is equal to sin theta plus cos theta, the sin theta divided by cos theta. Here we will consider tan theta as a given line segment. Tan theta is a line segment. Now tan theta is written as the tan theta by 1. This 1 is the L. That is, when L is the given line segment, we get tan theta as the output. When we will see tan theta by L is tan theta by 1, we will consider it as L tan theta by L, where L is converting into L tan theta. What does that mean? That means the base of the triangle is given, and we have constructed the perpendicular as the output line segment. That is written as tan theta, and the third line segment, that is the hypotenuse, is the complement line segment in that case. Now that was that we were talking about the left hand side of this expression. Now after equal to, there is a term called L sin theta by L cos theta. What does that mean? That means a simple story. Suppose we have to write it as a bigger thing. Suppose we have to write it like this, where we can think of it as a case where L tan theta, L sin theta is divided by L cos theta, L cos theta. We will consider that this L cos theta is the given line segment and L sin theta is the constructed line segment. We can think of it like this: both of these are actually constructed like this. Suppose this is constructed from L, and this below thing is also constructed from L. We will consider it like this, that L sin theta by L, and the cos theta is also constructed from the same L there. That is, it is also constructed from this L, and in that case we will understand it like as if the initial given line segment is constructing the cos theta, and if that same line segment L is constructing the sin theta. So L is the input for both of these GT simplex, whatever it is in the numerator or whatever is the denominator. After the output line segments are constructed, L is still there attached with both of these GT simplex, and the output line segment is sin theta, which is the perpendicular of the triangle, and at the bottom in the denominator the L cos theta is also constructed from L, and that is the output line segment for the GT simplex, which is at the denominator. Now this denominator is the base and the numerator is the perpendicular of the triangle, where L is the given line segment. Now the base is constructing the perpendicular. We will define it in that way. We will not tell that sin theta by cos theta. We will call it as the cos theta is the line segment, which is the output due to the L cos theta, and that output is the input now. And in the numerator, L sin theta is the output of the L sin theta, which is the perpendicular now. That is the output line segment due to the numerator GT simplex. And after doing this step, we will consider it as the output of the denominator is now the input of the whole GT simplex, and output of the numerator, output line segment of the numerator, is the final output of the numerator GT simplex. And in this interaction, the base is constructing perpendicular. That is the same story as the left side of the expression is saying. In this way, we will interpret every identities, and in this way, when the two ratios are said equal, we will consider that the left side is talking about some triangle, and right side is talking about some triangle, and several jungle of line segments are entangled with both of these triangles, whatever they are. But these two triangles which are interacting with equal to are similar. These kind of story are told in identities where there are multiple ratios are equated with the identities. So when the two expressions are said equal, either that is talking about two line segments are of equal length, or two angles are of equal length, or if these two cases are not satisfied, the third case is also very much valid. That is, the two ratios are equal, means left side is also talking about any triangle where several jungles of line segments are entangled with the triangle, whatever they are, and the right side is also talking about some triangle where also several jungles of line segments are entangled due to the simplexes or offsets, whatever they are, and they are all drawn in the dotted lines. But they are also important because several geometric inquiries can occur due to those jungles also. Their properties are also very important. But the identity is talking about the similarity condition of two triangles which are actually interacting through the equality symbols. These are the functional equality conditions in geometrifying trigonometry. These three geometric equality conditions are there, and there are several layers of equality also. Suppose we are taking a simple case. Suppose two line segments are equal, and how will you tell that these two line segments are equal? Sometimes the start point of one line segment is the end point of another line segment, and the end point of first line segment is the start point of the second line segment. It can also happen, but both of them have the same length. It can happen that the two line segments are of equal length, but they are perpendicular to each other. It can happen that two line segments are equal, but they are parallel and far distant away. But still the trigonometry expression will say that the equality holds. But geometrifying trigonometry will not get satisfied with this kind of equality. Geometrifying trigonometry says if two of the line segments are exactly overlapping on each other, then we will say it is the highest level of equality. And overlapping will also have the start point of first output, first line segment is overlapping on the first point of the second line segment, and end point of first line segment also overlaps with the end point of the end line segment. This is the best form of equality, but it rarely happens. We normally become happy in trigonometry when two line segments are of equal length, or two angles are of equal length, equal size, or if the two ratios are equal, we are happy with that. But geometrifying trigonometry never gets happy with these simple conclusions. Geometrifying trigonometry go deeper into that. Sometimes it finds some parallelogram, but still the opposite sides are equal and the equality is holding. But geometrifying trigonometry tries to find deeper conclusions on what kind of symmetry is interacting with what other kind of symmetry, what kind of gluing out of the four symmetries is doing the best output results, for what other kind of gluing when the other kind of simplex are glued in the different symmetries with the four symmetries, where which of the kind of the symmetric multiplication are the best options to choose as per the minimum energy principles, or what kind of graph theory problems are happening with the minimum distances or the moving salesperson problem that can get solved due to this, what kind of DNA structures will take the due to the least energy principles, due to the four configurations of the plus minus into divide alignments and gluing can get there. And all these deeper kind of queries, geometric intuition queries, and several kind of queries can come where we will find that when there are the ratios are equal, still there are jungles of line segments and jungles of points are there. And it can happen that there are 600 number of points, but out of that 480 number of points are all concentric. It can happen that 300 number of circles are covering all the points of the system. It can happen that the outside boundary of the GT simplex is overlapping hexagon. Ultimately, whatever we do, it is overlapping on a single hexagon and repeating over that continuously. And this kind of geometry we have seen when we are using the geometrifying trigonometry simulator, that is Autodesk forum. In Autodesk forum you will find, and a separate video also I have already shown, that when we construct the GT simplexes or locked sets, and when we take powers, and when we change theta, in several cases we get beautiful pictures where same pattern repeats one above another, and it is taking a finite shape, and there are very beautiful pictures which we can see. From that we can get different kind of conclusions, and ultimately sometimes it can happen that the summation of a series can have a finite value into some n, because it repeats n times over a single picture. Single perimeter is overlapped one another n number of times when we take nth power. So several kind of integrations we can do, and several natural summability conditions also occur. We are confident that with this kind of geometric interpretations, and with this kind of geometric constructions, with this kind of geometric development with trigonometry expressions, we can solve many kind of power series. We can find the summation of many kind of divergent series also, which were not possible before, until we were geometrically constructing the expressions. And these kind of things can open up many kind of facets of the mathematical analysis, and also for DNA structure developments or calculations of the minimum energy principles into the intercellular processes, or in the microbe cases. We can make the many predictive models on the geometric nature of the virus molecules. We can design the minimum energy principles with the geometric symmetry calculations on the virus molecules, so that we can prepare many kind of medicines also. We are thinking that these kind of quasi-crystal modeling systems and crystal modeling systems in the crystallography systems also, we can model many kind of molecules with these kind of minimum energy principles on the configuration choice systems. We can design many natural summability conditions of the power series, and our analysis world will also get many geometric views, and from the geometric queries will come out from the geometric pictures, geometric diagrams that will automatically generated from the trigonometry expressions. And we can do some left hand side is equal to right hand side. Now we are doing nth power on the left hand side and nth power on the right hand side, and we will get more number of jungles of the line segments and points, and from that we will get more number of properties of the concentric circles and the perimeters of the shapes. And for different values of the theta, we will see that the emerging natures of the calculus of different kinds of shapes will evolve from one kind of shape to another kind of shape. Sometimes you will see that there are some discontinuous pictures will turn into overlapped continuous pictures, and there with the simulator we play and we find several such intuitions out of that. And so I am sharing it in this video, that we can get different kind of insights that we were not getting yet before, because we were not solving the trigonometry problems actually in the geometry. From the day one, 3300 years, from the 3300 years, we have been using trigonometry, but we were not constructing all the things, because obviously the CAD was not there. I am standing on the shoulder of giants, and even on the CAD softwares, even on I am standing on the LLM models, and I am standing on the machine learning system, so I can visualize many more things. And I am the CAD programmer for 20 years and designing many bridges and the buildings and architectural things, so the visualizations are also there. And I am using the finite element analysis and Delaunay triangulations, and I am using SolidWorks, Lumineers, CATIA, and Tekla, AutoCAD, Blender, and many kind of such softwares, and all of these giants are there, and I am standing on their shoulder, so I can see the things that these kind of opportunities will open up, and which was not there before at the time of Hilbert. So I believe that if Isaac Newton could get AutoCAD, then he could develop these things much back, and we would get many kind of solutions much back. And it can happen that we could generate the medicines to resolve the virus, or we could find the medicines of cancer 60 years back, if AutoCAD system was there at the time of Newton. I believe so. Obviously, because Maxwell has made the reciprocal diagrams, Professor Cremona made the graphical statics, and David Hilbert could visualize these kind of things are necessary, and these kind of things are possible in geometry and imagination, he has already said. And Felix Klein was also very strongly proposed the Erlangen program in Göttingen in 1870-1880 time. So obviously these kind of things was possible if CAD systems was there, but things take time. Yes, obviously the world is not commutative. You cannot do the Newton then Einstein, and then you cannot say that Einstein then Newton. The things are not commutative in nature. So doing shortcut with the commutative law is a very long cut ultimately. That is one of the conclusion of geometrifying trigonometry. If we would take everything non-commutative from say 100 years, then it could happen that we could find the solution for cancer also, because we were not bothered with the non-commutative laws of geometric construction in the number system, and that has caused many disturbances in the growth of mankind, and that has caused many disturbances in solving problems. And in quantum mechanics also, I strongly believe that if we treat all wave equations and if we treat all Fourier series with non-commutative systems like that we have described here in geometrifying trigonometry, and if we can take care of the four symmetries instead of only one algebraic solution, then we can get the easy solutions for many kind of visualizations, and we can find many constructive inductive models of interpretations for explaining the entanglements and the laws of nature. I believe so that four symmetry is necessary to analyze at every stage of plus minus into divide, and non-commutative law, associative and distributive law are okay, but non-commutative law is very important to do every kind of analysis. I believe that our analysis of calculus will also take a newer domain, and we will get deeper views if we take care on the non-commutative with the four symmetries for every kind of reductions. And that is the final part of this video, where we have almost concluded that our geometrifying trigonometry works on these principles. And fractional power is a very odd kind of thing that we are not taking care right now, and we will rewrite any trigonometry expressions so that no fractional powers are there in the system, that we cannot handle the fractional powers yet, and after some research some new insights can come. Right now Sanjana's geometrifying trigonometry don't cover the fractional power. One more thing that I have to tell you, that whenever the sign on parenthesis starts and until that parenthesis end, whatever they are in between, it is a number, it is a pure number. Even any big expression is present there, we cannot handle that as an expression. We will consider it as a pure number which has only one meaning, that is an angle. Because when a sine, cos, sine, tan or sec, cosec, cot bracket is there, whatever in that bracket is there, it is a pure number. These two are very fundamental axioms of geometrifying trigonometry. First axiom is every of the GT simplexes or every of the locked sets for a given trigonometry expression are generated from only one line segment L. Second axiom is we will not take care of any fractional power. Third axiom is we will consider that whatever is inside the cos bracket, sine bracket, tan bracket, sec bracket, cosec bracket, cot bracket are pure numbers and representing the angle. The fourth axiom is non-commutative law, like sine theta into cos theta is not equal to cos theta into sine theta, because geometrically they are not same thing. Associative law holds, distributive law holds, okay, these things are there. And four symmetry, and the sixth problem is, the axiom 6 is that four symmetry is very necessary at every stage of plus minus into divide. So our syntax tree parsing systems will follow these kind of things, and line segment is the most fundamental interaction thing. It is like vector, but it is not vector, because it has one option that its start end points will change with the left hand side and the right hand side alignments are also changed. So four symmetries are there for every line segment, and every line segment don't come alone, it comes with at least one triangle. And every GT simplex always move with its output line segments, and we cannot move a single line segment until single line segment alone. It comes up with all the GT simplex line segments which are entangled with it, because we cannot split them out for every locked set or for every GT simplexes. These output line segments will interact, but it will carry all its entangled line segments together with it. And this is very important thing in GT simplex. And ultimately there are several theorems which are there where these interacting line segments and where these entangled line segments interact with each other and creates the different interesting shapes. And there are several kind of geometric theorems are coming up with these properties. For particular some values of theta, we see that only 6 number of equilateral triangles are forming with the entangled line segments. These kind of several theorems are there. And even the triangle centers, with the encyclopedia of triangle centers, we have seen the barycentric coordinates are there, and we can explain many kind of reasons of 9-point circle or the centroids, and many kind of properties of triangles, and many kind of solutions of triangles are also related with the geometric distribution of these entangled line segments, and those are also very big subjects there. And from those kind of pictures, I was guessing that someday we will find the structure of the DNA and the RNA with the minimum energy principles due to these force symmetry rules and the non-commutative rules. And that is also a very interesting subject, and I am very much wishful that someday we can explain the nature of the entanglements of the particles or the string theory through the geometric arrangements of these non-commutative behaviors, and force symmetry rules will play a very important role to analyze this kind of physical nature of the world. Thank you.